Let's take another look at this, or another example of this with our acetate ion. So here we have acetate. We have one oxygen up here and then an oxygen down here, and it's negatively charged, right? And so to this, we're going to add some acid, some H+, and this negative charge is going to go ahead and pick up this acid, right? Pick up this acid and get this H+. And then what we see experimentally, our products, we can actually label these oxygens. So we can tell which one's orange, which one's purple, right? We can tell that experimentally. And so we get the product that we expect, right? Which would be the hydrogen attaching to the negatively charged oxygen. But we also get something else. We get this product now too. Oops, flip the colors there. Where now our hydrogen is attached to our other oxygen. And in fact, we get them in a 50-50 mixture, right? And so you can tell that this is not really the real structure of the acetate ion. You have to think about its resonant structure, right? Its resonance structure. And so you could draw another resonance structure that looks something like this. Right, and this explains how you get the other mixture, right? And so let's take a look at a more detailed look into this, right? So we have our acetate ion, and the first thing that we have to realize is that all of these are actually sp2 hybridized carbons, or oxygens and carbons. We'll get into why a little bit later, but for now you're just going to have to believe me. They're all sp2 hybridized. And so let's think about what that means. So I'm going to draw oxygen, carbon, oxygen, right? We're just going to take a look at the three components that we're thinking about here. And so first thing we have here is all of these single bonds. We have a single bond here between the carbon and the oxygen and another single bond here, right? Those single bonds are sigma bonds. And remember, sigma bonds come from the hybridized orbital, so these come from the sp2 orbitals. All right, so there's an overlap there. There's that bond. There's an overlap there. There's that bond. And then these oxygens have lone pairs in their orbitals in the other sp2 orbitals. And this isn't totally accurate picture, right? But then there's another CH3 back here that's bonded to carbon's other sp2 orbital. But we'll just ignore that for right now. And then we have this double bond, right? The second out of the two bonds. And remember, this is a pi bond. And pi bonds come from the unhybridized orbitals. And so since these are all sp2 hybridized, they all have one unhybridized p orbital. And that's where these electrons are at. It's not that these electrons are only here and here, but they're actually throughout the whole system, right? We have this kind of 3 pi orbital bond where these electrons are just kind of hanging out over the whole area of these bonds, right? So these 2 electrons are delocalized over the system. And so the real structure is not really what it looks like when we're drawing these skeletal structures. Another example is the allyl cation. So we have a double bond and then another carbon with a positive charge. We can draw a resonance structure where the positive charge is now on the opposite side. And the same thing is happening here, right? We have carbon, carbon, carbon. We have some sigma bonds. And then we have some pi bonds. And the electron is delocalized over these pi bonds. Something like that, right? And so our Lewis structures don't completely show that. Our skeletal structures don't completely show that. If you think about a more advanced theory of bonding, molecular orbital theory, it actually has no problem showing this, right? So here's the molecular orbital for these 2 electrons, right? And you see that the electron is all throughout all 3 carbons, right? So what we say is that nature has no problem doing this. It is our model that is inadequate, right? It's not that nature's doing anything funky or that it's not supposed to do. It's just that our model is relatively simple, and so it just doesn't work well for this, right? So how do we do this? How do we kind of fix our model? Well, we just fix our model by thinking about resonance structures. And we don't explicitly do this, but we just kind of assume that our audience can do this, right? So as an organic chemist, you must see the truth, right? So when you see this allele cation, what you should be thinking about is this kind of delocalized positive charge, right? And so this is kind of what you want to think, right? Don't really think like this, think like this. But what we want to draw is actually this on the left and not the one on the right. The reason that we don't draw these structures like this is that it gets complicated really quickly. And so we just draw this and then assume that our audience is knowledgeable and can see the structure for what it really is, right? And so we need to get really good at this. Right? Because we need to be able to get good at this so we can see what the real molecule looks like, right? To see kind of the truth here. And so we'll spend the next couple of mini lectures here talking about resonance structures, what makes them good, what makes them bad, what things you can do, what things you can't do, that kind of thing. But at the end of the day, it's really going to come down to practice.